Here we are given that a block is released from rest and slides down a track with negligible friction, descending a vertical distance of 5 meters from its initial position to a point P. The block then slides on a horizontal surface where there's a friction. So there's a friction of 0.2, coefficient, the coefficient of friction is 0.2 here, static kinetic friction. And we have to find that after how much distance will this block stop. So this question is based on conservation of energy and probably again either work energy or Newton's law. So first I'm going to find the speed over here as soon as it reaches point P using energy conservation. So I'm going to say that mgh as an energy at this point, that is only potential, that's going to convert entirely into half mv squared, that is kinetic, right? So m and m is gone and I'm left with g is taken as 10, height is 5, that is equal to half v square. 5 times 2 is 10, 10 times 10 is 100, so 100 is v square, which means that v is just 10 meter per second. Now I'm gonna, either you can use, like I said, kinematics or work energy. I think I'm gonna use work energy power, that work done by all forces will be equal to the change in kinetic energy. So over here, there is only one force that is going to do the work, that is the friction force. So friction is here. So I'm going to say that the work done by the friction is going to be mu k times normal reaction times the displacement, and changes kinetic energy is final is 0 and initial is half mv square. So it looks like there was no need to actually find the v. We could have just substituted half mv squared directly. But anyway, it doesn't really matter. This is a dot product, by the way, and the angle between friction and displacement is 180 degrees. So we're going to write this as mu k Fn times displacement times cos 180, and cos 180 is just -1 is equal to half. Negative half m is not given to us, neither we need that, and v square is just 10 square. Now mu k is given to us as 0.2, normal reaction is mg, d is unknown, cos 180 is minus is equal to -1 half m 100 over here. M and m is gone. If we put g as 10, we are going to get negative 2d is equal to, I think, -50. So d will be equal to 25 over here. So this is the distance that it is going to travel, which is clearly option D over here. That should be our answer. All right, let's talk about the next question. In this one, we are given that there's a graph given to us, and then that graph is velocity versus time. And we are given that we have to find, the instruction says that the velocity of the function, the velocity as a function of time is given for a straight line motion, in which of the sections is the acceleration constant and non-zero. First off, obviously the acceleration is 0 wherever velocity is not changing. So these two cannot be the answer because the acceleration is 0 over here. If it has to be a constant, then we know that acceleration is given by what? dv over dt after all, correct? So if acceleration is a constant, dv over dt should be a constant, and this will be a constant only when v versus t will be a straight line. So it has to be either rs or st, right? And I think both works. Rs and st both works. The only difference is this is a negative acceleration, this is a positive acceleration, but they just need a non-zero. They're not talking about positive or negative, so I think option C works pretty well. Okay, net force F is exerted in a straight line given by this, where F is this, A is this, B is this. What is the change in momentum? We know that the change in momentum, also called impulse, is given by F dt integration, right? Integration is from 0 to 3, of course, so I'm going to integrate from 0 to 3. So the impulse is going to be F, which is A t square plus B, where what is 1, t square is t square, and B is again 1, dt, integrate from 0 to 3. So that's going to work as t square plus 1 dt from 0 to 3. So this will look like t cube over 3 plus t. Of course, you can use a calculator as well, guys. I'm just doing it manually because calculator is always allowed. If you put 3 here, 3 cube is 27, so 27 over 3 plus 3. And if you put 0, obviously you're just going to get 0. 3 times 9 is 27, and 9 plus 3 is just 12 over here. So I think I'm going to mark option B. That's the correct choice. Okay. A spherical star spinning at an angular velocity of omega suddenly collapses to half of its original radius without any loss of mass. Assume that the star has uniform density before and after. What is the angular velocity of the star after the collapse? So this is clearly based on conservation of angular momentum. Angular momentum is conserved because the net torque is zero, right? And what is angular momentum? Angular momentum is I omega. So I'm going to say that I1 omega 1 should be equal to I2 omega 2. And I, we know, is proportional to mr square, right? For a spherical object having a uniform density, to be precise, the formula is 2/5 mr square. But even if you don't remember this formula, you just have to remember that moment of inertia for a uniform object is always dependent on mr square for a solid object. So you're just going to replace I1 with m1 r1 square omega 1. Why this works is because I1 and I2 are at both the places. So whatever is the coefficient here is irrelevant because that's cancelled. Will be equal to m2 r2 square omega 2. It's given that there is no loss of mass, so m1 and m2 are equal, so they are basically cancelled. And omega drops to half, which means that omega 2 is omega 1 divided by 2. And r1 square, and what is r1 square? Um, um, I'm sorry, omega is not half, r is half. Omega is something that we need to find. So let me just correct that real quick. So R2 is actually R1 over 2. That's what happens here. And omega 2 is unknown. Omega 1 is as it is and R1 square is as it is. So R1 square omega 1 will be equal to R1 square over 4 omega 2. These two are gone. So the new angular speed is actually 4 times the initial angular speed. So I'm going to mark 4 as option D. That works. Okay. A pendulum is constructed by attaching a 1 kilogram sphere to the end of a light spring, okay, which is fixed to a ceiling, makes sense. A second 1 kilogram sphere is attached to the end of a spring, which is also fixed to the ceiling. The pendulum and spring have same length when in equilibrium, uh, and both spheres are displaced from equilibrium in the direction shown and oscillate with the same period. If 1 kilogram sphere is then replaced with a 2 kilogram sphere and the amplitude of the oscillations are unchanged, then which of the following is true about the period? We need to know the formula for the period for both, right? This one has 2 pi root L over G, and this one has 2 pi root M over K. If the amplitude is not changing and no other parameter is changing except the mass being doubled, right? So we can clearly see that the pendulum has nothing really to do with the mass. In this formula, you can see there's no mass, right? So it's going to remain the same for the pendulum. And this is definitely not proportional, but it's proportional to the square root, I can say. It's proportional to the square root of the mass. In other words, if the mass increases, then the period will also increase for the spring. And that gives us option B as the correct choice. So I'm going to mark option B over here. Okay. A heavy sign of mass M rests by two supporting wires between two buildings making an angle theta. What is the tension in each wire? Okay, since this is symmetric in nature, since the figure is symmetric in nature, I'm going to say that the tension is same in both the pieces at an angle, and obviously there is an mg. So this is the FBD. Doing a little bit of geometry here, if I draw this dotted line, then this angle will also be theta because they are alternate angles, right? So if I make the components now, the components are going to look like t cos theta from the left side, t cos theta from the right side, then t sine theta because of this tension going to the right, and t sine theta going to the left, and there is an mg over here. All I have to do is equate the vertical forces to each other and horizontal. Horizontal doesn't make any sense because obviously t sine theta and t sine theta is gone. So total upward force is 2t cos theta and downward force is mg. So the value of t is mg over 2 cos theta, which looks like option B. In an experiment, two blocks made of different materials are placed on the same wooden board, which is initially horizontal. The table shown provides three values for each block: mass, area, and coefficient of static friction. One end of the board is then slowly raised. Which of the following correctly identifies the block that will start sliding down first and includes an appropriate reasoning? If you guys remember this is a direct formula at an angle on an inclined plane actually. If this is a block, then what is the minimum angle at which it will start sliding down actually depends only and only on mu static, and is given by tan inverse mu. I don't know whether you guys are aware of this formula, but if you're not, I think you should memorize this. This is the minimum so-called critical angle at which this block will now start sliding down. As you can see, it's not dependent on mass, it's not dependent on area, just the value of mu s. So clearly, for tan inverse 0.2, it will return a smaller angle compared to tan inverse 0.4, meaning since tan inverse 0.2 is 11.8, so and this is 21.8, 11.3 and 21.8, it means that at 11.3 degrees, the block 1 will start slipping first because its coefficient of static friction is smaller. So it has to be option B. Okay, so about energy bar. The student lifts a ball straight upwards at a constant speed. The energy bar diagram represents the gravitational potential energy of the ball earth system and the kinetic energy of the ball at time t naught. Okay, fair enough. At a later time tf and at a later time tf, which of the following energy bar correctly represents the change in mechanical energy of the ball earth system for the time interval tf minus t naught? So isn't that a very straightforward question? I mean, they're just looking for the change of mechanical energy for the ball earth system. Ball earth means we have to take potential and kinetic energy both into account. The final mechanical energy is 1, 2, 3, and 1, 4 blocks. Initial mechanical energy is just 1 block. The difference is 4 minus 1, that is 3 blocks. So any option that has 3 blocks, that's my answer. Has to be option C, right? That should be the change in mechanical energy. Right. A uniform beam of length 0.6 meter and 4 kilogram is fixed to the wall by a pivot. All right. Okay, fair enough. The beam is held horizontally by a string fixed to the beam and the wall, and the block of 1 kilogram is attached to the end of the beam. Which of the following is nearest to the magnitude of the torque about the pivot exerted by the weight exerted by the weight of the block? Yeah, I don't really understand why they have given so much information when they are just looking for the torque exerted by this teeny tiny block. This is of 1 kilogram. It is exerting a force of 1 times 10, that is 10 Newton if we take G as 10. And the distance of the pivot between the pivot and the point of action is already given as 0.6 meters. So obviously the torque is as simple as RF sine theta. Theta is 90, so the answer is just 6 Newton meter. That should be the torque. That is option B. Right. Here we are given an outward machine. The block of mass m1 and m2 is attached by a thin string that passes over a circular wheel of mass m. Okay, this is not massless now. This is a mass m. The string does not slip and exerts forces T1 and T2. When the wheel is released from rest in this position, it undergoes an angular acceleration and rotates clockwise. Which of the following is correct about T1 and T2? Obviously, it makes sense that if it is rotating clockwise, don't you think T2 has to be greater than T1? Isn't that intuitive? Because if it is rotating clockwise, there is definitely a torque. Torque provided by the T2 must be greater than T1, right? Torque by T2 must be greater than torque by T1. And both T1 and T2 are providing the torque about the center. So the distance from the center is same for both, which means that T2 times R should be greater than T1 times R, which means that T2 should be greater than T1. Now the only question is whether which option is it, C or D? Because m1 is farther from the wheel? No. Because an unbalanced clockwise torque is needed to accelerate the wheel clockwise? Yes, that makes sense. That's what I was saying, that unbalanced torque is needed to accelerate it clockwise. Okay. Two identical blocks M1 and M2, sorry, block 1 and 2 are dropped from rest at different heights above a horizontal floor. One has speed V1 immediately before hitting, 2 has 2V1 immediately before the hitting. The work done by the gravity on block 1 as it falls is W1. What is the work done by the gravity on block 2? If we can get an idea about the change in potential energy, that is basically giving me an idea about the work by the gravity as well, right? So it starts from rest, and obviously they are dropped at rest at different heights. So I do not really know what their heights are. But let's say for block one, the initial potential energy is given by P1, kinetic is 0, and when hitting potential is 0 and kinetic is half mv1 square. Remember that the mass is same for both, right? So we are getting the initial potential energy as half mv1 square, and it's already given that the work done by the gravity in case 1 is w1. So we actually got an idea, although work done by the gravity and the change in potential energy are related by work done by a conservative force is negative of change in potential energy. But again, that negative sign doesn't really matter because I'm just trying to compare the numbers. So I can say, but I can still use the negative here. I can say that work 1 will be equal to negative of change in potential energy, final energy is 0, minus initial energy is P1. So it will again eventually come out as P1, which is half mv1 square. So that is given in a fancy way, we are given W1. Now we have to find block 2. For block 2, again we will do the initial potential is equal to half m, and the velocity is now 2v1. So that's going to give me 4 over 2, that is 2mv1 square. That is the value of P2. And what is half mv1 square? In fact, from here, can we manipulate this a little bit? Can I multiply both sides with 2 to write 2w1 as mv1 square, and this mv1 square I can sub in here. So that's going to look like P2 is equal to 2 times 2w1. So P2 is equal to 4w1. So that is actually the P2, and P2 is nothing but the work 2. So work 2 is actually 4 times work 1. That is option D. That should be the answer. Okay. A block is hung vertically from an ideal spring, and the block is pulled down and released and allowed to oscillate. The vertical position y as a function of time is shown in the graph. Which of the following options, the graph is right here, which of the following options represents the corresponding acceleration as a function of time? If we just remember the very basic condition for SHM, which is acceleration is proportional to minus x. In this case, it will be proportional to minus y because that's what they are. It's a vertical, movement. So all I have to do is just reflect this about x-axis because that's position, and that will give me acceleration, right? So if I reflect this about x-axis, I think I'm not going to get option B definitely, because this will come right over here between these two vertical lines. There will be a maxima, which is definitely not here, definitely not here. Clearly it's option A. Between these two lines it is maximum, and clearly these two looks reflected about the x-axis. A small rock is launched from the surface of a planet with no atmosphere. The initial speed is 2v escape. What is the speed of the rock when it is far away from the surface of the planet? This is based on energy conservation, since the initial speed is half v escape. So we are going to say that since it is launched from the surface of the planet, and we know that v escape for any planet is given by root of 2gm over r, right? I'm writing this for a reason. So can I say V escape square will be equal to 2gm over r? So can I say half of VE square is gm over r, right? Let's keep it aside. Now I'm going to conserve the energy because energy, it's something like this. This is a planet. This is where that is launched at 2 VE. And when it is far away means infinity, what is the speed over here? So at this point, what is the energy? Energy is kinetic, which is half m. M is the mass of this object times 2 VE square plus the energy of the planet and the mass, which is given by negative g capital M small m over r, will be equal to half mv square plus 0 because there is no energy when they are at an infinite distance. Now, this was the reason why I was finding gm over r, because just gm over r now you can sub in as half ve square. Okay, so 2 square is 4, 4 over 2 is 2. So 2 mve square minus half mve square. Why half mve square? This m remains as it is and half ve square is here, is equal to half mv square. M is gone. Let's multiply both sides with 2. So in fact, 2 minus 1 over 2 is 3 over 2. So 3 over 2 ve square is equal to half v square. Half and half is gone. If I take square root both the sides, then a square root of 3 ve will be equal to v. That is option D. That should be our final answer. All right. Two uniform disks A and B of mass m and radii 2r and r. The rotational inertia of the uniform disk of mass m and radius r is half mr square. A rotates about the center with omega naught and B is at rest. B is then released and falls onto disk and both spin together. What is the final angular velocity? This is clearly a question of conservation of momentum where I1 omega 1 should be equal to I1 plus omega 2 times omega, where I1 omega 1 is only for the disk A because the disk 2 is at rest. Okay, so already given that the general formula for the moment of inertia is half mr square. So for disk A it will be half m 2r square because its radius is 2r and omega 1 is just omega naught. When they merge or rotate together, their moment of inertia will be added. So half m2r square should be added with half mr square, and this omega is as it is. Okay, this is just a matter of decoration. So 2 square is 4, 4 over 2 is 2. So 2mr square omega naught will be equal to 4 over 2 is 2 again, 2mr square plus half mr square omega. 2 plus half is 5 over 2, so 5 over 2 mr square omega should be equal to 2 mr square omega naught. Mr square is gone. Multiply both sides with 2 to get 4. 4 omega naught is equal to 5 omega and divide both sides with 5. So 4 over 5 omega naught is equal to 5. So 4 over 5 omega naught is option C. I think that should be our answer. Finally, the last question is a truck of MT is initially at rest, okay, with a load of sand of initial mass ms. At t equal to 0, the truck is pushed forward by a constant force F naught and the sand begins to leave the truck as shown. The mass of the sand that has left the truck as a function of time is given by Ct, where C is a positive constant. At T1, there is no sand left in the truck. Which of the following nearly describes the velocity of the truck as a function of time? So I know that after T1, there is no sand, so the mass is just mt. Mt as in not empty, it's m sub t. So the acceleration is just f over mt. That is going to be a constant value. And if the acceleration is constant, then dv over dt is a constant value, which means that v versus t should be a straight line. A straight line as in like this with some slope, not as in horizontal line. So that obviously rules out option B and option C. Obviously, how can it be option A? I mean, it cannot really follow the same trajectory before it because the mass is continuously changing, right? How can the acceleration be same? And if acceleration is not constant, how can the velocity linearly increase with time? So by elimination, option C is correct. But yes, C also makes sense because it has to be quadratic in nature. Why? Because with time the mass is decreasing, so the acceleration is increasing, so with time the velocity is also increasing. So C makes best sense.